Sustainable, safe, and low-cost energy storage systems are essential for large-scale electrical energy storage. Herein, we report a sodium, Na-ion hybrid electrolyte battery with a replaceable cathode system, which is separated from the Na metal anode by a Na superionic conducting ceramic. By using a fast Na-ion intercalating nickel hexacyanoferrate, NiHCF, cathode along with an eco-friendly seawater catholyte, we demonstrate good cycling performance with an average discharge voltage of 3.4 V and capacity retention 80% over 100 cycles and 60% over 200 cycle. Remarkably, such high capacity retention is observed for both the initial as well as replaced cathodes. Moreover, a Na metal-free hybrid electrolyte battery containing hard carbon as the anode exhibits an energy density of 146 Wh/kg1 at a current density of 10 mAh/1, which is comparable to that of lead-acid batteries and much higher than that of conventional aqueous Na-ion batteries. These results pave the way for further advances in sustainable energy storage technology. The demand for renewable energy sources such as solar and wind energy is rapidly increasing, owing to the need for replacing fossil fuels, in order to combat climate change. A very important auxiliary technology for supporting the development of renewable energy is electrical energy storage systems, EESs, which are very important for the extensive and efficient deployment of renewable energy and for ensuring time and geographically dependent supply of electrical energy. Over the past several decades, lithium-ion batteries, LIBs, have been developed as powerful energy storage systems and have demonstrated high energy density and good cycling stability. LIBs find applications in most portable electronic devices today. However, the availability of lithium resources in the future may not be sufficient for meeting the huge demand created by the emerging large-scale electrical energy storage systems. In recent times, sodium-ion batteries, SiBs, have been considered as alternatives to LIBs, owing to the abundant availability of sodium at low costs, which makes them more suitable for large-scale electrical energy storage systems. The most well-known sodium-based energy storage systems include NAS and Ni Class II batteries, Zebra. However, the operating temperature of these batteries is greater than 300 degrees C, which introduces problems related to thermal stability and safety. Owing to these potential issues, special care may be required in the handling of some battery components. Besides these high-temperature batteries, room temperature SiBs have also been extensively studied over the past few years. However, regardless of whether high-temperature or room temperature SiBs are used, thermal management will be a major problem in large-scale electrical energy storage systems because the charging and discharging processes would produce a significant amount of heat similar to LIBs. This could create safety issues, which is the main reason why the application of LIBs is not yet established in large-scale electrical energy storage systems. Aqueous rechargeable sodium-ion batteries, ARSBs, have attracted much attention as a promising alternative owing to advantages such as low cost, green, and safety. However, one of the primary disadvantages of aqueous rechargeable sodium-ion batteries is that they deliver a relatively low energy density owing to the limited working voltage, 2V, due to the decomposition of water. So, the enhancement of cell voltage has been a major challenge. However, the working voltage of ARSBs can be improved by using NaSiCon, Na3Zr2Si2Po12, as the solid electrolyte, which separates the moisture-sensitive Na metal anode, in a non-aqueous electrolyte, from the aqueous electrolyte, water. In the present work, we have designed a sodium-ion hybrid electrolyte battery system in which a Na intercalating/deintercalating nickel hexacyanoferrate, NiHCF, electrode in seawater is used as the cathode, Na metal in an organic electrolyte is used as the anode, and Na superionic ceramic conductor, NaSiCon, Na3Zr2Si2Po12, is used as a separator between the two electrodes. In this battery system, the cathode can be easily replaced at the end of cycle life because of the open-type cathode system, and separate cooling systems are not necessary for safety reasons, since the battery system uses seawater during operation. The battery exhibits good cycling performance with an average voltage of 3.4 V and capacity retention 80% over 100 cycles and 60% over 200 cycles, for both the initial as well as replaced cathodes. Additionally, a metal-free sodium-ion hybrid electrolyte battery was also fabricated using hard carbon as the anode, with an energy density of 146 Wh/kg1 at a current density of 10 mAh/1. These findings pave the way for a new method to construct cost-effective and eco-friendly large-scale battery systems with high energy density. Nickel hexacyanoferrate, NiHCF, nanoparticles were synthesized via a one-step co-precipitation reaction. First, 6 mol of Ni, NO3, 26H2O, alpha ESR, was dissolved in 60 ml of distilled water under stirring to obtain a transparent solution, solution A. Subsequently, 3 mol of Na4Fe, Cn, 6, sigma Aldrich, was dissolved in 140 ml of distilled water, solution B. Next, solution A was added to solution B dropwise using a syringe and the solution mixture was sonicated for 1H.